Can you guys hear me? By the way, thank you for properly pronounce my surname. That is the first time that happens. My dad will be proud. Okay, so um, today I'm going to talk you about a practical introduction to category theory, right? But I'm going to be honest with you. I know nothing about it. So I started my career as a Java developer, like I believe most of the people in the audience are. And when I started at university, they keep saying, okay, Gang of 4 is the way. Learn the patterns and reuse them all over the place. And then I started using Scala, and people start talking about these crazy mathematical things that I couldn't understand, and I really wished to be a mathematician because my path from Java to Scala, I believe, would have been 20 times easier. So what am I doing here? So I took some time because I was really curious about why everybody was so passionate about all these crazy concepts with crazy words. And I went away and studied a little bit. And I really enjoyed the keynote from this morning from Kevin. I do agree with him. You don't need to know category theory to code in Scala. So again, why am I talking about this? Because I studied it a little bit, and I had a lot of moments that were mind-blowing. Suddenly, everything was clear, and my Scala code had a completely different meaning. So this is going to be a practical introduction about category theory. Why practical? Because I'm not a mathematician. I'm probably not the right person to talk to you about the mathematical laws behind it. But my goal today is to give you some sort of intuition of how things work and why category theory is so important. In particular, we will do a link between cats. Thank you, Miles, for cats. There is a fairly popular library in Scala that maps a lot of category theory concepts into our code. Joke of this conference, of this talk. So it's called cats, but actually, all the main maintainers of cats are dog lovers. They spend all their time publishing dog pictures on Twitter. They are actually not into cats. The reason why it's called cats is because it's from categories. So don't worry, there are not going to be cat pictures in this presentation. There are not going to be dog pictures in this presentation. So we are safe from those kind of things. So let's start a little bit about why category theory is important. And the first thing is, when we code, we actually teach the computer how we reason. So in a way, we are translating how we think into a program. So how do we reason, right? So for example, we had to walk from the train station to here. So what we did was, okay, this is our task. So I'm gonna split it down in smaller tasks. So I'm gonna go and take Via Giolitti, and then at some point I will turn left, and then I will turn right. So basically, what we did is that we divided the way we think in smaller tasks, and we then composed them together. But we didn't just do that. We didn't think, okay, I'm going to walk, so I'm going to put my feet in this way and then in that way. We know how we walk, right? We don't think about it. We just do it. So we abstracted out a lot of details that we didn't really care about it. We just focused on step 1, step 2, step 3, and I will arrive at the conference and enjoy this day. So composition and abstraction is kind of the key of what we do. Object-oriented programming is about composition and abstraction as well, right? Where the composition is about the objects, and the abstraction is about not exactly knowing what an object does. Sorry. We don't know the details of that specific action, just that he does something. In functional programming, the composition is about the functions, and the abstraction is about mathematical laws. So why category theory? Category theory is exactly that. It studies how to compose things that are completely abstract. So for me, the name was a little bit scary at the beginning, because category, what the hell is that? So I'm going to change the name. I'm going to call it arrow theory. We are going to see in a second what a category is. But actually, what you are going to see is that all the time, we are going to talk about these arrows. We're not going to never look at what an object actually is, but we are always going to look at how these objects are connected together. All good? Cool. So let's start. What's a category? Well, it's nothing really too complex, right? It's a bunch of objects, where objects, I mean the most generic object possible, that are linked by an arrow. What is an object? I don't know. It could be anything, really. What's an arrow? I don't know. It's just something that has a direction that points to objects. Obviously, we are programmers, so our task is actually a lot easier, because we are always going to focus about types and functions. But in theory, category can be anything. So nothing too crazy, right? Sounds reasonable. And there are some rules that are going to be part of our game. The first rule is composition law. So if you have an F, that is something that connects an A and a B, and if you have a G that connects a B and a C, then you know that there is the equivalent arrow that is the result of the composition between F and G. Little detail about this little O. Mathematicians are right, are weird. So basically, they read it G after F. So you first look at this, and then you go back. They do it reverse, right? So it's weird. But after a while, you get used to it. So basically, F and then G is the same of G after F. So this is really important law. We should definitely remember this. The second law that is really important is the identity law, where basically we say that if we take this F to go from A to B, it's basically the same of saying, okay, I'm going to take this little arrow that basically does nothing. I just stay where I am, and then take F. And so F after ID of A is the same of F. But it's also the same is the true for the opposite. So if I take F and I go in B, and then I take the identity of B, so I don't go anywhere, I still end up in B, right? It makes sense. It's just a lot of weird stuff to say exactly ID does nothing. Last rule of our game, when we compose things, the composition must be associative. What does it mean, really? That we don't care about parentheses. So it means, basically, that if I go for the green path, so I say H after G, and then I do after F, it's the same of saying, okay, I'm going to do H after G after F. Really complex stuff. It's just saying that the black path and the green path are the same. You still start from A, and you are going to end up in D. Yeah? All good so far? So, rules. identity, composition, and associativity. Okay, but what do we care, right? Well, this is actually something that we know already, right? We do it all the time, so this can be an example, right? So we know that given any string, we can define a function that it could be called size, that it will return an int. And given an int, we could define another function, for example, bigger than 2, that will return a Boolean, right? And we compose these two functions and get a beautiful function that is saying, from a string, returns a Boolean by saying size bigger than 2, right? We do this all the time. And as well, with identity, for example, for string, one of the possible ways of having a function identity is to say, no matter what the string I have, just concatenate it with the empty string, and I will get the same string back, right? So this is something that we do all the time. We don't realize we do it, but it's really familiar to us, right? So let's look at something a little bit more interesting. What's the simplest type of category that you can think of? It's probably the category with just one object, right? So you basically don't go anywhere. You always stay there. So again, the same rules as before. It must be a category, right? So it must have an identity. And composition law means that if I have an arrow that is an A, and if I have an arrow that is a B, then I can compose them together and basically have a new arrow for free. Okay, that's cool. Does this remind anything that we might be used to? Let's see a practical example. So this is exactly the same that we just saw, but we have that the operation is a plus. All the arrows are numbers. In this case, they are integers. And the ID, we choose 0 as the ID. So the identity law is basically saying that when we combine any number with 0, we get the number back. So 1 plus 0 is 1, that is 0 plus 1, and so on and so forth, right? This is basic mathematics for us. And the composition law tells us that if we combine 1 with the operation plus, if we combine 1 and 2 with the operation plus, we get a new arrow, right? That is free. That's cool. So we just found a representation, a really simple representation for all the natural numbers, right? That's pretty cool. So what is this? This is called, in category theory, a monoid. So this code has been adapted from cats. But basically what we said is that we have an identity, and in cats they call it empty. And we have an operation that, given two things, it will return one thing back. They call it combine, right? So congratulations, you just discovered what a monoid is. So when the cool kids say monoid, they basically mean this. So the idea of being able of combining two things into one. You're just smashing things together. Cool, let's do some more cool stuff. So we have this beautiful category that is, given a flower, I have a function to transform that flower into a triangle. Can somehow create a category from another category? Well, yes, we can. So for example, I can define a function that basically copies the objects. So a flower will be transformed through this function into a flower with a box. Okay. Same for the triangle. But we want still to have a category back. So we don't have to, we need to copy both the objects and the arrows. So a lot of fancy words, but basically what we're saying is that if we know how to transform a flower into a triangle, then we know how to transform a triangle in a box, a flower in a box into a triangle in a box. Right? That kind of rings a bell, right? Can we think of something familiar that we do in Scala that kind of has this shape? So if you know how to transform A to B, then you know how to do it box of A to box of B. Well, yeah, we know what it is, right? For example, instead of saying box, let's say option, right? So basically, this is just the map function. So examples of containers that we have in Scala, right? We have options, right? Everyone knows options is the idea of a value that might or might not be there. Future, it's the idea of having something that takes a while. Try, something that could explode. List, something that contains 0 or multiple values of the same type, and so on and so forth. So a container is just something that gives us more information about the data that it contains. And this, for me, when studying category theory, was the first moment when I had my real mind-blowing. You know, everything suddenly was clear. Basically, what we're saying is that now we don't just have data, but we have information about our data. So for example, if we have an option, we know that the data might be missing, it's not guaranteed that it's going to be there. So this is extremely useful because we have a clear information about the content of our box and the meaning of our box. So, how cool kids call this? This is a functor. So basically, the functor is the idea of having some extra information about your data. I've changed this slightly from the CATS code, but basically it's exactly what we're saying. We're saying that if we have a box of A, and we have a function that will transform that A into a B, then we know how to do it for, we know how to get a box of B. Yeah? All good so far? Cool. We do this all the time, right? Again, you don't need to know all these details to know how to use map in Scala. But it's good to know why it's called map and how it works. Okay, cool. What if you have something like this? So a box really can contain whatever you want, right? It can contain a value, it could contain a function. So what we have seen so far is that we know how to get a box out of any data, and we know how to open a box and see what's inside. So what if you have this scenario where you have a function in a box and you have a value? With the operation that we have so far, there isn't much you can do, because all you can do really is just open a box. So what you need to do is to first open all the boxes, then somehow combine the data together, and then put them in a new box, right? So we need to add something more. Functors is not enough anymore. So if we look at the CATS code, again, this is a simplified version. This is called applicative and has pure, that is basically put everything in a new box, right? So it takes a value A and it produces a box of A. And then we have this weird operation that is basically saying, if I have everything to a box, I know how to combine them together. And we can rewrite map in terms of these two operations, right? So again, what do we care? This basically means that first we are gonna look inside our containers, all of them, and then we are gonna try to combine them together. So this basically means that doesn't matter in which order you are gonna apply, you are gonna open your boxes, because you are gonna open them anyway before doing anything else. Okay, that's cool. Everyone with me so far? Yeah? That's cool. So, obviously, you know, this is a simple case scenario. What happens if your function that it's in a box takes multiple values? Well, it's not a problem, right? So what we're saying is that now I have a function that takes 2 values and produces a b. So now you have to open 3 boxes rather than just 2. Not a problem. We can extend the function to support up to 22 values. So it's just called differently, basically. So you need to know how many parameters your function takes and call the right method. Okay, and now the moment that everyone doesn't understand, but it's actually so simple. Okay, so we have, the rules that we have so far is we know how to build a box, we know how to open a box, and we know how to combine things within a box. But what if I open my box and I apply a function and my function returns a box itself, right? I will be in this state where I have a box in a box. But I don't really know how to deal with that, right? Because I don't know how to throw away one box. All I have to do is that I can open it once and move the context to another box. So what do we do? I mean, we need to have a way of, if I have 2 boxes, then I need to just have 1 box. It's, I would say, basically the same of what we saw before with the monoid. We have 2 instances of something, and we want to smash them together and just get 1 out of it. So yeah, it turns out that you just need to define a function that does that. And that function is called flatten. All flatten does is, given a box inside the box, it returns a box. Why do we care? Well, because this gives us a monad. We are going to see in a second why a monad is important to us. But basically, it allows us to compose things in order. Let's see how exactly it works. So you have a box that contains an A, and then, sorry, little detail. Because map and then flatten are oftenly used together, actually, there is an alias that is called flatmap. Basically, what it does is that given a box of A and a function that returns a box of B, it will return a box of B. Okay. So why do we care about monads, right? It's such a crazy word, and we don't really. Why do we care? So we have a box of A, and we use flatmap to apply a function that goes from A to a box of B, right? And that returns a box of B. We can do it again, and from a box of B, using flatmap, we can get a box of C. Do it again, and from a C, we can get a box of D. So basically what we have done is that in order, in sequential order, we change the content of our box from A to D. So the order here does matter a lot. So we know how to do this, right? In Scala, we have this beautiful thing that is called for comprehension that is basically just syntactic sugar to represent exactly that. And if you look at the code, it's split in multiple lines. So in a way, it's exactly the same as the drawing that I just showed to you, right? Things are in this order, A, B, C, D. So is the code, right? So hopefully, I managed to give you some intuition of how these things work. But just to quickly wrap up, what is category theory? Category theory is something crazy that just studies how abstract things are combined together. What's a monoid? It's something that takes two values and smash them together. So you get two values combined into one. Functors is just a way of adding information about your data. So we do this all the time, right? We want to know how what our data does, how our data is executed. And applicative is just a way of combining all these boxes together in a way that is completely independent, meaning the order doesn't matter. We are going to go through all of them no matter what. And finally, monad is just doing all these operations inside a box in a specific sequence. So hopefully, now you know a little bit more about these crazy words, and you will understand when people mention these principles. Is this everything there is to know to cats or category theory in general? Well, absolutely not. I did this on purpose to scare you. This is Rob Norris, our crazy Rob Norris, that did a drawing of all the type classes that are in cats. You probably are not going to be able to see it, but you can see that there is a lot more to know than just those few principles that we have seen. But those few principles that we have seen will let you understand a little bit better why we write the code that we write in that way. So what if you got completely lost? There is only one thing that I would ask you to really remember about this talk, is sometimes it's useful just to forget about everything else and just ask yourself, how do I want my types to compose together? That can dramatically improve not only the performance, but also the quality of your code. So, this was a practical introduction, but obviously, what happens if you want to know more? There are a lot of details, a lot of laws that we didn't mention on purpose. So these are my favorite sources to get more information about category theory. The first one is a talk by Philip Walder that did Lambda World. It was extremely fun, and it goes into the details of what a category is. Then we have Mr. Bartosz that did a few free videos on YouTube about category theory. It goes quite deeply into the mathematical details of it. But the thing that I really like about his videos is that at the end of each video, he does this kind of practical intuition that kind of remind ourselves that at the end of the day, we are programmers, not mathematicians. Then, if you guys want to have a look at all the crazy things that there are in cats, this is the link where you can find the image that I showed to you from Rob Norris. And also, when I started this journey, the first place where I started was actually the cats documentation. You will be surprised, it's actually quite accessible. So if you don't have a lot of time, but you want to know exactly why a specific type class is there, why should I use it, I think the cats documentation is a great place to be. So that was everything for me. Hopefully I didn't bore you too much, and I gave you some intuition of why certain things do matter in functional programming. I'm going to post these slides on Twitter, so that's my Twitter handle. And if you want, have a look at my blog, and thank you.